So I'm making this recording to cover the material we were going to go over in our chat this week. I wasn't able to log into the chat session. I don't know why, so I apologize for that. But this video will cover the same material that we were going to go over in the chat. So we're starting a new cycle, cycle 4, and we're going to go over 2 sections today. The first one is called Outwit and Outlast, and we're going to talk about writing and solving proportions. And so we're going to form the ratio. Let's just jump in and do a problem. So here's a proportion that's given to you, and we want to solve for x. So the first thing we're going to do here is cross multiply. So 3 times 21 equals 7x. And then we're going to divide both sides by 7. And so x equals 9. And then we can check. And that checks. Okay, let's try another one. This one's got the variable on both sides. We're still going to start out by cross multiplying. And we're going to distribute on the left side here. And then we want to combine the x terms, so we're going to add 6x to both sides. And then we're going to divide by 9. And so we come up with x equals 12. And again, we want to go back and check and make sure that checks. And it does. All right, let's try another one. This time, notice the variable's in the denominator, but that's okay. We can still solve it. So we're going to cross multiply again. So -3 times the x minus 1 equals 5 times x plus 1. Distribute on both sides. Okay, now we want to combine like terms, so we're going to go ahead and move the x's to the right, and then we'll move the constants to the left. So when we move 3x to we add 3x to both sides, we end up with 3 equals, and combine the x terms here, 8x plus 5. Subtract 5 from both sides. -2 equals 8. Divide both sides by 8 and simplify. And so we get x equals -1/4. And again, we want to make sure we go back and check. Now, just an interesting observation that apportionment of whole number quantities according to rules has been part of the U.S. House of Representatives. And so every 10 years when we do a census, we look at the population and determine how we're going to allocate the 435 seats total. And that's based on allocations. And you could take a look at this website if you like. It gives you some interesting information on how that works. And again, from your book, there's a little thing here, and they're using proportions again. So 435 seats to the whole population is equal to the seats for state X relative to the size of state X. Now, of course, we have to round here. So there's actually slightly different or more complicated formulas that are used, but this is similar to what happens when they do reconfigure the apportionment for the House of Representatives. Okay, so let's take a look at an application problem. So it says a designer is drawing a scale model of a living room, and the scale is 1 inch on the plan equals 1 foot in the living room. If a couch is 6 foot 8 inches long, how long will it be on the plans? Okay, so first thing we notice is that our scaling here has gone on the plan from inches to feet, and we've got the sofa in feet and inches, so we want to convert it to feet in order to set up the proportions. So 6 foot 8 inches is equal to 6 times 12 is 72. This should say 72 plus 8. I'll have to fix that. Equals 80 inches. And then if we divide by 12, we come up with 6.67 feet. So now I can set up my proportions. Form the ratio. So 1/4 is to 1 as x, which is what I'm trying to find, is to the length of the sofa. So this is the plan. This is real world. This is the plan. This is real world. And remember, my answer x here is going to be in inches, not in feet. So I'm going to cross multiply. So cross multiply, and I'm done. 1.67 inches. So 1 2/3 inches is how long the sofa will be on the plan. All right, and then 4.5, this is one of our introductions to probability and statistics that we're going to cover in this course. And this is on probability. And the section starts out by talking about theoretical probability. And theoretical probability is where we know the outcomes, they're generally equally likely, and we can work the problems. We can work on problems without actually doing an experiment. So if you think about rolling a die or tossing a coin, we know how many outcomes there are and how likely they are. So let's talk about probability. We talk about events in probability. We use capital letters. And the probability of an event E is written as P of E, right here. An event is an outcome of an experiment that is conducted. So let's say, for instance, we're rolling a die and we let the outcome E be that we get an even number when we roll the die. Probabilities are from 0% to 100%, but they can also be listed as fractions or decimals between 0 and 1. A probability cannot be greater than 1 or less than 0. And when we use mathematical notation, we can write this probability like this. Probability of E is greater than or equal to 0, less than or equal to 1. An event that has a probability of 0 or 0% is known as impossible. For instance, when I roll a die, what's the probability that I get a 7? It's 0, so that's impossible. While a probability of 100% represents a certain or sure event. So again, rolling the die, what's the probability I get a number less than 7? It's going to be 1 or 100%, so that's a certain or sure event. So to find the theoretical probability of an event E with equally likely outcomes, we create this ratio. So for my example previously, if I roll a die and I want to know the probability I get an even outcome, the numerator here would become 3, because the even outcomes are 2, 4, and 6, out of the total possible outcomes, which is 6, so 3 out of 6 or 1/2. When we list all the possible outcomes for an experiment, we're finding the sample space. The number of items in the sample space gives the denominator to the ratio above. For example, and again we're doing the rolling the die here, we want to find the probability of rolling a 5. So here's my sample space, 1 through 6. How many outcomes are the ones we want? Just one, that says a 5. So the probability of rolling a 5 is 1 out of 6. The probability of an event occurring plus the probability of it not occurring will always add to 1. So for example, if there's a 70% chance of rain, then there's a 30% chance that it will not rain. So I mentioned before, we can write probabilities as fractions, decimals, or percents. And we're going to complete this little table here. And in each case, they've given me a different format for the probability. So here it's 1/4. So to get to the decimal, I simply divide 4 into 1 and I get 0.25. And then for the percent, I just multiply the decimal by 100. And now this time they've given me the decimal, so I could write this as 6/10, so 6 over 10, or 3 over 5. And then to get a percent, we multiply this again by 100, so we get 60%. On the last row, they've given me the percent, 75%, which I could write as 75 out of 100, or 3/4. And then the decimal is going to be 0.75. So let's try a couple applications. Balls numbered 1 to 20 are placed in a box. One ball will be randomly drawn. Find the following probabilities. What's the probability that we get an even number? Okay, half of the balls are even, so that probability is going to be 0.5 or 50%. What's the probability that we draw a number greater than 16? Okay, there are 3 numbers. Actually, there should be 4 numbers. It should be 4. 4 out of 20. It should be 20%. I will fix that. It should be 4 out of 20 because the numbers are 17, 18, 19, and 20. What's the probability that I draw an even prime number? Okay, even, we know what an even number is. Prime number means it's only divisible by 1 and itself. And so the only even prime number is 2, so that probability is 1 out of 20, which is 0.05 or 5%. What's the probability I draw a number greater than 20? That's 0 because there are no numbers greater than 20. Okay, list the outcomes for rolling 2 fair die, 1 red, 1 blue, and 1 red. And so I've given you a handout in this module that shows both card decks and also rolling die. So we see here there are 36 outcomes. 6 times 6, there's 36 total outcomes. Okay, let's work a couple problems here. How many outcomes have a sum of 5? So by sum, we mean we look at the faces on the die. So here the sum is 2, 3, 4, and we want 5. So here's a sum of 5 here. 4 plus 1 is 5. If I go over here in the same row, I notice the sums are going up. But if I look diagonally, 3 plus 2 is 5, 2 plus 3 is 5, 1 plus 4 is 5. So I've got 4 out of how many outcomes? 36. So the probability is 1/9. A student answered the question this way. The student said there are 11 different sums. So if I look on the table here, the sums I can get range from 2 all the way up to 12. So there's 11 different sums. And he said that since there's 11 and we're rolling 2, the probability of getting a sum of 5 is that's only one of the sums out of 11. Does this make sense? Why or why not? Okay, this doesn't make sense because there's more than one way to get a sum of 5, and there's more than one way to get a sum of 6. And remember, the probability is the number of outcomes that fit the criteria divided by the total number of outcomes in the sample space. So it has to be 4 out of 36 or 1 out of 9. And I should go back for a second also and mention, I did say this, but the sums, the different sums are not equally likely. If they were, we could say this was true, but they're not. There's only one way to get a 2 and there's only one way to get a 12. But there's 4 ways to get a 5, so we have to use 5 out of 36. I'm sorry, 4 out of 36. Suppose there's a raffle with numbered tickets. One ticket will be randomly drawn from a hat. Your ticket is number 121. Find the following probabilities. If there are 200 tickets, what is your chance of winning? Okay, there's 200 to pick from, and how many are going to be winners? 1. So the probability of winning here is going to be 1 out of 200 with the decimal of 0.005 multiplied by 100 to get the percent, which is 0.5%. If there are 400 tickets, what is your chance of winning? Okay, 1 out of 400, divide to get the decimal 0.0025, and then multiply by 100 to get 0.025%. If there are 1,000 tickets, what is your chance of winning? 1 out of 1,000, divide by 100, 0.001, divide by 1,000 rather, 0.001, which is 0.1%. What happens to your chance of winning as the number of tickets increases? Your chance of winning is going down. If there are 150 tickets sold in the raffle, the same setup we had here, how many tickets will you have to buy to have a 10% chance of winning? Okay, what's the probability of winning here? It's 1 out of 500, or 150 rather. All right, which is also 0.67%. So if I buy 15 tickets, 15 times 0.67% gives me 10%. Another way you could look at it is just say, what's 10% of 150? 15 tickets. Experimental probability. Okay, experimental probability is where we actually have to conduct the experiment to find the probabilities. The probability ratio is going to be the same, but here we have to actually see how frequent or how likely something did occur. So for instance, if we do a poll right now to ask people who they're going to vote for president, we would come up with a likelihood of somebody voting for Hillary Clinton or Donald Trump, but we actually have to do the experiment to come up with the probabilities. So let's try one here. So here's a little table. There's a student council president election at Sage College. 80 students were polled and asked who they would vote for, and here's the results. And if we pick one student at random from this college, determine the probabilities. What's the probability the student planned to vote for Allison? So 22 students said Allison, so it's going to be 22 over 80, or 11 over 40, or 0.275, or 27.5%. What's the probability the student planned to vote for Kimberly? So 20 people said they'd vote for Kimberly, so 20 over 80, 1/4, 0.25, or 25%. Suppose there's a weekly raffle with 200 tickets sold each week. You play every week for 1 year. If you win twice, what was your experimental probability of winning? Okay, so you won 2 times over the course of a year. It's a weekly drawing, so 2 out of 52, or 0.038, or 3.8%, about 4% of the time. What is your theoretical probability of winning each weekly raffle? Okay, so for each week, 200 tickets are sold, you buy 1, so your theoretical probability is 1 out of 200, or 0.005, or about a half of 0.5% of the time. So what's interesting on that problem is, let's just go back for a second, is it's the same scenario but 2 different ways of looking at it. We looked at it as an experimental probability, and then we looked at it as a theoretical probability of winning each week. Okay, a bag contains 7 red, 2 blue, and 1 green marble. What's the probability of choosing a marble that is not blue? Okay, there are 10 marbles in there, and 2 of them are not blue. So there's 2 ways I could do this. How many are not blue? 8. So the probability of not blue is 8 over 10, or 4 out of 5, 0.8, or 80%. I could also remember the probability of an event happening plus the probability of it not happening has to equal 1. So if I know there's 2 blue, 2 out of 10 is 0.2. So the probability of not blue must be 0.8. So I actually have another way to work that problem. A meteorologist reports the probability of a hurricane this season is 15%. What is the chance that there will not be a hurricane? Okay, probability of it happening plus probability not happening has to equal 1. So if there's a 15% chance of a hurricane, there's an 85% chance there will not be a hurricane. A local restaurant is running a dart competition for which the contestants will be blindfolded. The owners will use a target below. The shaded area is the winner. And they want you to find out what's the probability the contestant will win. Okay, so this is a review actually of what we learned in geometry. So we can find the area of the square and the area of the circle, and we notice the square is inside of the circle, so it's less than the whole circle. So then we can do the probability as the green area divided by the whole area. All right, so the circle area, remember your formula for circle, pi r squared, and in this case, we're doing the circle here. The diameter was 18, so the radius is 9, so it's 81 pi, and the square is just going to be 6 by 6 or 36. And then we're going to do the probability, which is the ratio, 36, the area of the square, divided by the area of the circle, and it comes out to be a little bit more than a 14% chance that you'll hit that area. So let's explore the relationship, just to end this section here, between theoretical and experimental probabilities. For a fair coin, the theoretical probability of getting ahead is 1/2 or 0.5. Now you can go to this website here and flip coins as many as you like. Try flipping 10 times, 20 times, 30 times. Overall, are you going to end up with a 0.5 probability if you do 10 flips, 20 flips, 30 flips? Probably not. But the more flips you do, the closer and closer you're going to get to the theoretical probability. So experimental probability will get closer and closer to the theoretical the larger your sample size is. And that's one of the things you want to look at when you're looking at a survey or a poll results, is that you have an adequate sample size. So if you're asking people who they're going to vote for president, you don't want to ask 100 people. You'll see that most polls nowadays interview about 1,000 people. But again, the larger your sample size, the closer and closer the experimental probability, in this case the poll result, will get to the theoretical probability, which is what we're trying to estimate actually when we do an experiment or conduct a survey, because we don't know the theoretical probability. So hopefully this will help you with your work this week. And again, I apologize, I don't know what happened with my online site, but hopefully it'll be resolved before we have a chat again next week. So have a great week.